Hello, I'm John Killian.
And I'm David Altenhofen.
And this is the video on the Frequency Matcher 2000.
And today we're going to feature the lucky contestants of David Altenhofen with forward cap.
And David Altenhofen with backwards cap.
It should be a fun adventure. Stay tuned. You ready to start?
You win!
Now you must be wondering, how does one make such an amazing game? Well, first off, you have to have this superb display, the victory light, and your score popping up, and of course some motivational comments to go along. Now, this is just the front panel, and it's really none of the meat or behind the scenes work. This is just what everyone sees. This case structure here, resetting the motor after the competition has ceased. Other than that, it's really pretty straightforward and epic.
Now, with all great sound matching games, you have to have a way to generate the signal and record the player's voice and give it a score. And so to do this, we used Professor Vonk's patented method of generating a simulated signal between 200 Hz and 500 Hz. And then we play that signal to the player, who then gives their best shot at matching it. We compare the dominant frequency of the player's voice to the waveform After that, we compare the player's dominant frequency to the frequency outputted and generate a score based off how they compare. In this case, the highest score is 3, the lowest score is 0. Back to you. We needed a way to differentiate between the two players, so we took the iteration count and divided it by 2 and took the remainder, so it would be odd player and even player. If the remainder was 1, you know it was an odd number, and so player 1, and if it was even, you know the remainder would be 0, and so player 2. That gives us our true or false statement.
I hope you're ready to learn about how we control the direction of our motor and how big of steps it took. This is our stepper motor program, which we will use to tell our motor how many steps it should turn as well as what direction it should turn. We can use this to keep score for both players by switching our direction of the motor for when our points need to be awarded to one player or the other player. In the program, we used 3 different digital DAC outputs. These were used to control the motor direction and to tell it what size step to take for the motor, with one of the outputs being connected to a true statement and the other being connected to a false statement. Next, we inserted our photo sensor sub-VI, which I'll talk about how we made it later in the video. And we connected this to a statement that said true or false if it is dark, and we also connected this to our end game and our status of the game updater. Now it's time to learn how we created our photo sensor sub-VI. In order to tell when our game is done, we are using a flag on the end of our stepper motor, which will cover our photo resistor that we used on the board. This will change its resistance, it'll increase it, and this increased resistance will cause a greater voltage drop across the photo resistor, which we're using the DAC to sense the increase in voltage drop. When the increase in voltage drop is detected, it will tell our circuit to end by saying that the photoresistor is dark on top. This will end our circuit and tell our program to end because the game is done. We saved this as a sub-VI and used it in our stepper motor program.